Hello, physics students. This week we are gonna speed things up by talking about acceleration. And if you don't get that pun, well, then you're about to. So let's start with a little bit of a review from the things we covered last week. We covered six major topics, and we're going to talk about them all in relationship to this problem. So we have a person. They walk 10 meters from the front door to their mailbox in 5 seconds. They then walk back towards their door in 5 seconds. Then they take a break for 5 seconds. So this is motion, correct? And there's three distinct forms of motion. They are moving forwards, then they move on backwards, and then they come to a rest. So those are the three parts of the motion we see here. Remember, we talked kind of a little bit of higher order thinking of like, how do we really know he's moving? Well, like there would usually be some kind of indicators like in his perception of moving, like he's getting closer to the mailbox or he's getting farther away from his house when he's moving. And so we are defining our coordinate system to just be helpful here. We're making 0 his house, 10 the mailbox, and making things nice and simple for us. But I could also have just as easily called this 11, and just as easily called this 16, and just as easily called this 21. And no, there's really no difference in the motion just because I call them a different thing. As long as I'm consistent, we can call it whatever. So we're going to do it easier though and do 0, 5, and 10. So let's talk about distance. Distance is always a positive value, the sum of all the parts. The total distance traveled over this whole time is 15 meters. He goes 10 forwards, and then he goes 5 backwards. All together, that is 15. We do not subtract ever for distance because it's always just a sum. I could also do it over the distance parts. For part A, he traveled 10 meters. For part B, he traveled 5 meters. For part C, he went 0 meters. So we could break it down or we can do it all together. Same is true for displacement, indication of how far away something ended up from where it started. If it's positive if an object moved forwards, negative if it moved backwards. So we see for this case, the total displacement is only 5. Even though he really moved another 5 because he went 10 initially and then he went backwards 5, well, that cancels and he ended up 5 meters from where he started. There was other stuff that went on there, but displacement doesn't tell us about the other stuff. It tells us that he ended up 5 meters away from where he started. It also tells us that he ended up positive 5 meters away from where he started. And again, it's up to us really at the beginning to define what that means to be positive, but we did just that with the number line, right? Did just that with the number line. Setting up 0 to be here, 5 here, and 10 here. Well, that just gave me an initial positive direction towards the right, which is an easy thing to do. But just like I called this 11, 16, and 21, I could have also just called this 0, this -5, and this -10. And then I would get opposite answers, but it would make sense in my own reference frame. But again, I don't want to confuse you with too many reference frames here. We're going to stick with 0, 5, and 10. Clear the pen. There we go. 0, 5, and 10, and we'll stick with what we know. See, this guy moves forward again, positive displacement, negative displacement, and then 0 displacement for that last part. That's what I was saying here. We could analyze it. So initially positive 10, then it's -5, and then all together. And then the last step is 0 displacement. For speed, a person walks 10 meters from the front door. The speed, and he does so in 5 seconds, speed's just distance over time. So in A, we know that speed, how fast was he going initially? Well, 2 meters per second. In B, when he's moving backwards, he goes backwards 5 meters in 5 seconds. Should I be positive, negative? Doesn't matter. The negative, I should say, does not matter. Matters that it's positive or negative. We get just 1 meter per second. And then what about C? Well, in C, we're not moving at all. So those are the speeds for each 3 part. And we could do that over each part or for the whole time. What would the speed be? The total average speed. Average speed is just our total distance over the total time. Total time, which is 15 over 15, right? 15 over 20. 20 seconds passes altogether. 15 over 15. I can't read. 15 over 15. Because each section lasts 5 seconds. So we'd have a total speed of 1 altogether. All right, velocity. Velocity is displacement over time, so it can be positive or negative, and that depends on that. Positive or negative tells us about the direction of motion. We can't actually have a negative speed because you're either moving or you're not moving, but we can move forwards and backwards. So, and then just like with speed, we can do it over each part or individually. If I wanted to do A, I'd have a velocity of +2. You don't have to write that positive, but you can. For B, we'd have a velocity of -1. For C, we'd have a velocity of 0 meters per second. How is that any different from what we had gotten before? Just that negative for the backwards velocity, but that negative tells us information about how it's moving. What about the total velocity over the whole time? That is going to be different. AVG average V is delta X over T. What's my total displacement? Well, we already said it was 5. That's still over 15. So 5 over 15 is going to be my 5 over 15 is going to be my average velocity, which is different than the value that I got last time, which was 15 over 15, and I got 1. So average speeds and velocities can often come out to be different values. Even if the parts that we got here, here, and here were essentially the same numbers, this negative really ends up making a difference in the long run. And then finally, we talked about PT graphs last week. So if we have a person doing this and I wanted to graph this motion, well, I can do so on a position versus time graph. We always plot time on the x-axis and position on the y-axis. Should always put our units so we know, even though I kind of labeled it down there. Where do we start at? Well, in this case, we are starting at 0 at a time equals 0. And then what are we doing here? Well, we walk 10 meters forwards and it takes us 5 seconds. So that person 5 seconds later, where are they? Well, they are now at the 10 meter mark. What do they then do? Well, then they turn around and walk backwards 5 meters and it takes them 5 seconds to do so. So 10 seconds after the person had began walking, they are at a position of 5 meters. What did they do for that last 5 seconds? They stand there. Why did my thing drop? They just stand at rest, and we get a nice horizontal line there. So our position versus time graph can take all of this information and just put it into a nice, easy graph. And as long as we know how to read it, that's helpful and an easier way to transmit a lot of information rather than texting it, putting it all into text and numbers. Okay, so that was the review of what we've done last week. Let's get into the stuff for this week. So, acceleration. We know that velocity measures a change in an object's position over time, but velocity is not always constant. And we have a value called acceleration to measure the change in a velocity over time. So just like how velocity is equal to, I'm going to make that a vector, is equal to delta x over t, well, we also have this acceleration, which is equal to delta v over t. We can call that delta t2. So velocity is a change in position over time, and acceleration is change in velocity over time. And we need to remember that velocity here is a vector. And so both change in speed can cause a change in velocity. Like your velocity, if you go from having positive to, say your initial velocity is positive 2 meters per second, and your final velocity is negative 2 meters per second. Well, that's a change in velocity. So that's not a change in speed initially, because it's both 2, but the velocity, there is a change in direction. So doing either changes in speed or changes in direction both cause an acceleration. Remember the symbol delta? We call that delta V over delta T is always just final minus initial. So if I know that this change happened too in a time that lasted 4 seconds, well then I always do final minus initial to get my change in anything, whether that be velocity or position. Position was the same as always xf minus xi. Anytime you see change, it's always final minus initial. All right, think about this. Do you feel velocity? What do we mean by that? Do you feel yourself moving? Think right now. Are you moving? You could be. I don't know what you're doing right now. But do you feel it if you are? If you say, I'm not moving, so no, I don't feel it, but I would feel it if I was, would you? Because we talked about the whole planet, remember, and you are constantly moving at any given time. The planet is moving around in a big circle. You are the planet. spins, and then it moves in a big circle, and then that big circle is not a common circle either. You are constantly moving, and you never feel it. You never feel the whole planet moving through the Earth. You may think, well, I'd feel it if like I move along the Earth. You kind of, sort of, like you don't really tell that you are moving. You feel the changes from motion because you never actually travel at a perfectly constant velocity. Same as if you're in a car going 50 miles per hour. It's pretty easy not to feel yourself moving or not be reminded that you are. It's pretty easy to just like fall asleep in the back of a car if you close your eyes and forget that you're back there. But do you feel it if that car is going to crash into, well, that's a poor statement. Do you feel it if your car changes speed? Well, yeah, you do feel that. Imagine slamming on the brakes going 50 miles per hour. You are going to feel a quite drastic change in that velocity. In the pit of your stomach, you are going to feel that. The human body does not detect constant velocity. It's actually not a human body thing. It's a pretty impossible thing to have a sense of just velocity. But what you can have a sense of is an acceleration. And we'll talk about why that is and the difference in our next unit when we talk about dynamics. But for now, we can detect acceleration when there is a change in velocity. Anytime your velocity changes, think about it in both cases in a car. Your car speeds up. What happens to you? You get put into the back seat because your body is resisting that change. And the same as when you slow down, your body flies forward, and that's why we need a seatbelt to keep you from flying through the windshield. Even lighter versions of this, just like getting on the ground and like standing up is a change in your body's motion. Going from a rest position to a non-rest position takes effort and energy to do, and you have a good sense of that. I talked about all those things. And I didn't talk about, and just changing your direction. If you are going at a constant speed but moving around in a circle, like when a car rounds a corner, you feel that too. Your body is also resisting that change. And your body's like over here, it's trying to like keep traveling in that straight line, but your door has to like keep you pushing you in the circle that your car wants to travel in. So you can feel that too in the pit of your stomach, which is why roller coasters work really well. But if you have a roller coaster with a fun loop-de-loop and you're going at this whole circle at a constant speed, you still feel a big change because of the centripetal acceleration. All right, so acceleration, we just talked about that. We can define it a little bit more clearly. It's change in velocity over time. We can use this nice little equation here. If you have a final velocity and initial, we can just find what the difference between it is. How much did the velocity change? And how much time did that take? We measure acceleration. We measure velocity in meters per second. We measure time in just seconds. So meters per second, meters per second is the same as meters per second squared. And this is our SI unit of acceleration. It's essentially the only one that we are ever going to use in this course. It requires us then that we need to make sure velocity is in meters per second and time is in seconds. If you have velocity in miles per hour and you have if you have velocity in miles per hour and you have time in minutes, well, those units are not going to work out. So make sure you're paying attention to your units and that you're using the right ones, the SI units and only SI units. Does acceleration always speed an object up? Well, no. If you are moving forwards and you have an acceleration that is also forwards, that's when you are going to speed up. But if you're moving forwards but you hit the brakes, well, you're going to have an acceleration that's backwards and you are going to have a speed that decreases. The reverse is also true. If you were moving this way and you have an acceleration this way, this is going to be form of speed up. And if you are moving backwards but you have an acceleration forwards, you have a negative velocity, negative v, but a positive a, well, this is going to be a slowdown. Anytime acceleration and velocity are opposites, you're slowing. Anytime they're in the same direction, they are speeding up. Let's talk a little bit about terminology. Acceleration refers to a change in velocity of any direction. And so anytime you have a change, it can be a positive, it can be an acceleration that causes a speed up or a slowdown. Any kind of change in velocity is an acceleration. We have a term, and I'm not like crazy about it, called deceleration, and that specifically refers to a negative change in velocity, meaning like a slowing down. I don't like it because it can be confusing depending on our motions. So like technically both of these are correct to say. If we're moving forwards, it's correct to say that you have an acceleration of negative 4.3. That would mean you are moving forwards and your acceleration is backwards, and like that means that you could infer from this that you're slowing down. But also, if you're moving forwards and you're just told you have a deceleration of 4.3, then that means you're slowing down. Like you don't have to put that negative there anymore because you covered it in the deceleration. This kind of gets tricky because then if we think about the reverse, now we're moving backwards. And what kind of an acceleration would make us slow down? Well, a positive acceleration would make us slow down. We would need an acceleration to the right to make us slow down. So having an acceleration of 4.3 would make us slow down, and we would understand that. But also having a deceleration of 4.3 is also correct. Both of these being positive, this also means that we would slow down, because deceleration always means the acceleration is in whatever direction it needs to be to make a slowdown happen. But acceleration, and it's not, the confusing part is it's not one or the other. It's not like you're accelerating or decelerating. Acceleration can be any positive or negative change, and it will be used like that, because this is really the correct terminology for any kind of change. Deceleration is unnecessary. We don't need to use this term, but the term does get used, especially in the more modern world and less of the scientific one. But know the difference between both of these sayings, please, and what I mean by acceleration and deceleration. All right, let's do some practice problems. A bear sitting at rest smells a hiker and accelerates to 9 meters per second in 3 seconds. What was the bear's acceleration? Well, let us start first with a formula. Formulas are always helpful. Let me start by identifying some variables. What was my initial velocity in this case? 0. He was at rest. What was my final velocity? 9. What was my time? 3. 0, 9, and 3. Can I turn these numbers together and figure out an acceleration? Well, acceleration is my change in velocity, which is always final minus initial, over my time. I get 9 over 3 altogether, and I get a final acceleration of 3 meters per second squared. All right, so let's take a look at the second problem here. If we have a car going 10 meters per second, decelerates at 2 meters per second squared, how long will it take for the car to reach 4 meters per second? So we want to use the same kind of formula. A is equal to delta V over T. Easy enough. What do I know? I know my acceleration is 2, positive 2, negative 2. I think it should be negative 2 here. And that is because my initial velocity is 10, positive 10. So for my acceleration to slow me down, I'm going to need a negative acceleration. That's some of the trickiness of the decelerates word there. I know A needs to be negative. And I want to know how long is it going to take, so I know I'm solving for time, for the car to reach 4 meters per second. Right, final speed to be 4. Now let's plug these things into my equation. A is equal to negative 2. Delta V is final minus initial over T. Can I solve this equation now for T? I'm just plugging things in. I want to figure out what is T. I absolutely can. And the thing to remember here is that you need to get T out of the denominator. To solve this correctly, we got to multiply both sides by T. And again, why do I do that? So now let's take a look at what I have. I now have negative 2T is equal to 4 minus 10 is negative 6. I could have done the 4 minus 10, but then I would have had negative 2 equals negative 6 over T. And if you think, oh, I just divide both sides by 6, well, that doesn't leave T by itself on the right-hand side. That would give you 1 over T, not what we want here. What we want to do is get T in the numerator by itself on the other side of the equation. And then now what do I do to both sides? Now I just got to divide both sides by negative 2. And notice how those negatives cancel, which it makes a lot of sense that they do, or else we should be confused because there's no such thing as negative 3 seconds, but there is such thing as 3 seconds. So what's my answer? Well, decelerating, like our change in velocity was negative 6. How long does it take to reach that, to make that change happen? It takes 3 seconds at the acceleration rate that we had indicated. 3 seconds. All right, so what I want you guys to do right now, here's a little overview of displacement, velocity, and acceleration, formulas for each one of them. Remember that you can rearrange these formulas. So like displacement, we really just have one, delta x is equal to this. But my velocity equation, v equals delta x over t, well, I could rearrange this equation and solve for delta x. I could also rearrange this equation and solve for t. Same with my acceleration, I can solve for delta v, and I can solve for t. If you are given, like in the last problem, we knew that we needed to find time, and we were given a change in velocity and an acceleration. We could have skipped the step of solving and or rearranging our equation and just plugged into this equation. Totally up to you how you want to do it, but all of these equations are available to you. Displacement is defined as how far away you are from where you started, and it is the area under a velocity time curve, but we are not going to talk about that until the next video. I have for you 3 problems. I would love for you guys to pause this video right now and see if you can solve these 3 problems on your own. Here are the answers to those 3 problems. We got 0.5 meters per second squared, a ball rolling down the hill, but it ends up being 15 meters per second, and that meteor would take about 614 days to reach the Earth. All right, so we're using acceleration, and we're using all of our equations here. Figure out what you know and determine the correct equation that you need to use. Here's another 3 sets of problems. Again, I encourage you, pause the video, see if you can get these on your own. Here are the answers that you should have received. And then I have 2 more problems for you. Finally, 2 more problems. Can you get these ones on your own? If you can, these are the good ones. If you can do these ones, you can do that quiz no problem. Pause the video and let's see. All right, here are those final 2 answers. That is everything that I have for you guys today. If you are concerned about any one of those 8 practice problems, you are welcome to send me an email or come in a small group or large group, ask me questions. I love getting questions, however they may come, and I'd love to help you guys out with any of these questions.